When you've got a bit of electronics knowledge, people tend to bring you some weird things for repair, particularly when they've not been able to get them repaired elsewhere. And in this case, I was asked if I could take a look at this AVR. Now, AVR stands for Automatic Voltage Regulator, and it's used in generators for varying the voltage that comes out them and providing a feedback loop so that you can set the voltage and no matter what the load is, it will try and keep that voltage fairly constant. Now, this is old. I was just looking at this and realised there's a date in it, 27/6/1978. So this is almost, but not quite, but almost 40 years old. So it's actually doing pretty well to have got to this level before it finally broke down. Now, to give you an idea of what an AVR does, where's a notepad? Where's a notepad? If you have a generator, let's tame this down a bit, shall we? That's better. If you have a generator, it generally has the rotating rotor, which has got a magnetic field in it, say north at that end, south at the end, and the axle in the middle, and then it's got this sort of caps at the end, and if it was a single phase generator, you would just have a coil. This is somewhat simplified. It's actually, these tend to have lots of coils around them, and sometimes several coils on what's called the rotor. I should point at this point in time, the rotor is the bit of the generator that rotates. The stator windings are the bits of the generator that stay stationary. So rotor rotates, stator stationary. So if it was a single phase generator, you'd have this magnetic field passing by this coil and generating an AC alternating voltage out of it. If it's a three-phase generator, all you do is you have three sets of those coils spaced 120 degrees apart. So to vary the voltage out, you vary the magnetic strength in this, because if that was just a fixed magnet, then it would the actual voltage would depend on the load that was being applied. So they have a winding round this, and it usually comes out through slip rings, and one side of the winding will be positive, one will be negative, and that goes back to an excitation control unit. Now, the excitation control unit, in some of the generators, they have a little auxiliary winding for the feedback. But in the case of this one, it's quite interesting because they've not. That feedback winding would normally just get, the output would be rectified, smoothed, and then there'd be a transistor would simply switch this in, and it wouldn't, although you get some that vary it in an analog manner, most of them it just pulses on and off or pulses modulates, because it reduces dissipation in the transistor, and all you're really doing is adjusting the magnetic field in this. It's a sort of thing that if you give it a pulse, it will hold a magnetic field for a while in the core, particularly because it's not an alternating magnet, it is just, in this case, it's a DC magnet. But in the case of this circuit, it's quite clever because they've got the circuit here, if that's one of the phases going out, they've just tapped off that. And that's not just giving the actual voltage reference what's going out, say in this instance 240 volts, which it probably will be because it is a generator of that era. But that is then used to power the circuitry. But in this case, to actually excite this, they take the live connection and they connect the excitation winding to it, that's the bit in there, and then they're using a thyristor down to neutral, and they're phase angle controlling it, and there's a back EMF diode across the coil here. So it's sensing the voltage that's coming from the generator, and if the voltage is too low, it fires this thyristor. It uses an element of phase angle control to actually increase the magnetic field on this core, which is rotating, and that then brings the voltage up, and as soon as the voltage is high enough, it either reduces or stops providing excitation to it, and there'll be a sort of happy balance and equilibrium. So now we know what it's supposed to do, and I have to say I'm not a huge expert in generators. I've always tended to avoid. The fairground guys used to say, can you take a look at our AVRs? And I used to politely decline because I was a bit worried about the fact that if you made a mistake and it provided too much excitation, you could end up blowing all the lamps in a fairground ride, which would not be pretty. But in this case, it's not such a critical situation, and unit, it's just not, it's obsolete. You know, the company Marcon Engineering, I don't know if they even exist anymore. And the generator it's designed for is kind of obsolete as well. So it's a case that there is no real choice but to repair it or find an alternative system that could be put in. So the circuitry in this breaks down in this sort of format. There's a common sort of, say, a neutral connection here, and live comes in, and it goes through this resistor, which is the power supply section. It goes through this diode for basically a very simple single-phase rectification. So half-wave rectification is what I'm trying to say there. Gets capped at about 10 volts by this Zener diode. Goes through this diode and then goes to this capacitor, and that generates, for the whole circuitry, it generates 10 volts minus the diode drops, so that's about, say, 9.4 volts, and that's what powers the circuitry. There are two chips. One is a traditional SIM41, which is an op-amp, and that's basically a little chip that compares two input voltages, and depending on if one's higher or lower than the other, the output will change state. It's a very simple sort of comparator or voltage comparing device. The other chip is a hex Schmidt trigger, and that basically, it's 6 inverting gates. If you put a sort of high level in, it will come out low, but they've got a threshold so that as your voltage goes in, it suddenly the output suddenly changes state, and then you have to come back down below that to change it back. And they've just used that as a general sort of for timing purposes and to square up the signal for driving the thyristor here. The thyristor is being driven through this pulse transformer, which the chip is driving a signal to this transistor here, which fires a pulse transformer, and that just it basically amplifies the current from the circuitry to give a nice decisive pulse to the thyristor here. There's quite a few suppression capacitors and metal oxide resistors, and this is the back EMF diode that's actually across the excitation windings. So this device is quite clever in the sense that it takes the supply in, it gets the timing reference, because this unit also shuts off, if it detects the generator slowing down, it will, instead of trying to keep the voltage up, it will detect that the generator is running below the correct speed, and it will actually turn the excitation off completely, because otherwise, if you were trying to put the full voltage out as the generator ran down, you'd end up with this circuitry working really hard to keep that magnet excited with a higher magnetic field. And also, if the generator is putting out 240 volts at 10 hertz, it's not going to be, it's going to upset a lot of electronic appliances, transformers or chokes or ballasts in them. So the other connection here, it uses the voltage sensing, and for this it actually goes out through a link. I've got it linked out here, but it goes across this link and comes into the sense circuitry, and that's what the op-amp's for. What it's doing, it's detecting through these two resistors are acting in series, they're acting as part of a potential divider, and then there's an adjustable part of the divider, and then some filtering with capacitors. And what that's doing is it's detecting the 240 volts or whatever you set this potentiometer for. So this unit has 3 settings on it. It's got the voltage setting for what you want to come out the generator. It's got the stability setting, and I think, without actually a schematic, without actually knowing, without being able to see the live operation of this unit, what it's doing, and maybe even putting an oscilloscope on it, I reckon that this thing just means that it stops any sudden transitions of the output. It means that it avoids, shall we say, ramping up and down of the voltage. Basically, you tune that. It seems to be very much a thing, according to the manual, that you just adjust it by feel on site. And I'm guessing what it's going to do is it's going to just make it's going to be the feedback time to the magnetic field from this, that by adjusting it, if it was too sensitive, the voltage would ramp up and down. But if it was too insensitive, it would slowly cycle up and down, but you just get it to the point that it just balances out. The other setting is the cutoff. What's it called here? Does it say? Yes, underspeed. And it's got this cute little ceramic LED. I've only ever seen one of these little ceramic LEDs before, but it's a ceramic base with the red top. And that is actually a red LED. Very rare, old-fashioned red LED from that era. And that lights to show that the generator is underspeed. And initially, when you set this for the speed that's required, as the generator runs down, that LED will initially come on, and then if it goes down any further, then it'll suddenly just kill all the excitation. Now, I've got a light bulb connected to this, and I'm about to power it up just to show you basically what happens. But I would like to point out that if you're actually testing these things, the recommended approach is to use a isolation transformer. Oh, let me get the notepad in again. And the reason for an isolation transformer is safety. If you've got a main supply coming in to your workbench, and one leg of it, say that's live, that's neutral, the neutral is by default referenced usually to ground just for safety reasons. And it means that if you get a circuit like this connected directly to the mains, then if you touch part of that circuitry, you could get a shock to ground. So what an isolation transformer does, it basically takes 240 in our case 240, puts 240 back out, but isolates it completely from the grounded side, which means that even if you touched one connection in this, you wouldn't get a shock to ground. It still means you can still get a shock hand to hand, live to neutral, but there's no reference to ground just locally at your bench. So what they recommend is using this arrangement, plus they recommend having a variac, which is a variable transformer with one connection going to the test board, and then the other wiper connection that goes along the windings of the transformer coming to the other connection. But in this case, I've not got a variac here. I've got one in Glasgow somewhere, but I've not got it here, so I can't test that. But I do have a known 240 volt supply coming from the mains, which is non-isolated, so I'm just going to mention that again, that if you're ever doing anything like this, you have to keep in mind that the circuit board is live at mains voltage. So that is also at the desired frequency, which is, in this case, 50 Hz. I've connected across the excitation windings a lamp. It's another common test technique. You basically use the lamp as a visual indication of the feedback that would go to the windings. So if I turn this on, actually before I turn it on, I'm going to do that little routine thing. I make sure there's no metal lying on the bench. Everything's clear underneath. Yep. Okay, I can turn it on now. And this is where, if it does provide excitation, it's going to be flickery because it is only half wave, because this thyristor here is only controlling half the sine wave. So if I adjusted the voltage to the point that it was actually looking for the excitation, it has just ramped in. You can see the flicker. I can see the flicker because that is half wave and it is shimmering visibly. But if I then turned that to the point that, you know, I turned the voltage down, that it wasn't needing as much excitation, that will just gradually fade away, and it will basically just stop providing excitation. And it seems to ramp it in and out, but it doesn't seem to let you just tweak it. It's very slow. It's got this ballistic response that I presume is adjusted by this potentiometer here. I don't want to mess things too much. I've marked the circuit board, but I've marked all the original settings because it's already calibrated for a transform, but now some components have been changed. It's going to have to be reset up anyway. If I set this so it is actually putting output, and I change the over and under speed detection, say underspeed detection, if I wind that, is it that way? The red LED is lit now. It doesn't look lit because it's a very old-fashioned LED, and it's very dim. And the excitation has been killed. Now I've turned it back, the excitation has been restored. So the fault. Well, initially when you get something like this and you've got no schematics or anything like that, all you can really do is change what you believe would be the suspect components, particularly if you don't 100% know what the fault was. So this one was not providing excitation, but that could be that the sense circuit was faulty, or it could be that the output circuitry was faulty. So I routinely changed all the semiconductor components. I changed the thyristor on the output. I changed the protection diode, the back EMF diode, because it was just easy to do. I changed some of the suppression capacitor components. I changed the electrolytic capacitors. This is the power supply one, and this is one that's used for stability, I think. I think it just provides a local voltage reference on this op-amp. I also changed both the chips. I put them in sockets. Not sure that was such a great idea, given that this unit is in a sort of fairly harsh environment, and it's very clear the thing has been absolutely doused in lacquer. It's been conformally coated in the past, but that's not so easy with the chips and sockets. But I just wanted the option to change them, particularly because this one was an older style Motorola chip. It was a hex Schmidt trigger inverter, and it was not really possible to get those. The only ones I could find were from dubious sources that looked as though they may just be fake, so I'm not 100%, I wasn't confident, but it was suggested that since it is a pin-for-pin compatible with the 40106, which is a standard and readily available logic gate, I put that in instead. It does have a slightly wider hysteresis, but that probably isn't that critical. I have dug out the original chip, because I kept all the original components. I put it in, and I compared the behaviour, and it looks as though this is just purely a threshold. It's just to square up the output. But anyway, I did those things, and then we went and tested a bench with a variac, and nothing happened. And it was like, oh, that's annoying. Because now it means we have to start looking for stuff that's more likely to be a passive component, like a capacitor or a resistor. And the fault did turn out to be a resistor. A resistor, this one down here, 68K, that had gone completely open circuit. And it had slight tarnishing at the end, but corrosion had crept up and actually gone into the end of the resistor and caused it to fail. So all the components, all the resistors in the same area as that, I swapped them out. Any that showed tarnishing have now been changed like for like to make sure it's sort of got a new lease of life. So all these old capacitors here are all testing out perfectly. These ones are testing, well, these ones are the new ones. Everything is now pretty much, all the semiconductors have been changed. Most of the resistors have been changed. Fundamentally, it's going to give it a new lease of life. We're going to try it out, put it in situation, check it out, and that should be it. It's probably going to be ready for another 40 years. Albeit it really needs some conformal coating. But certainly in this case, I think the person who owns that generator will just be glad if they can get a few more years out of it, because it's got to that stage that it is on its last legs anyway. But yeah, that was an interesting little job. It was certainly interesting to take a look at. And it's that old thing that sometimes it's the least suspicious components. I mean, it's very rare that resistors fail, but just sometimes they do fail. And the only way to actually test that in the end is to get a meter and just see if the resistors, keep in mind there's other circuitry in line as well with them, which can skew the readings, but it's to take a meter and just see if they're anywhere near where they should be. And if anything's suspicious, take it out of circuit and check it, and that's what revealed the fault.